Okay, now for the third and last Jamboard part of Lecture 1, Week 6, looking at Taylor and Maclaurin series. So you may have noticed in the last few slides we were talking a little bit about approximating a function. So this Taylor series at 0, or the Maclaurin series, is when you take a function f and then you say, okay, the 0th order approximation is that this function is exactly just the same value everywhere, and that's the value it has at 0. And this first order approximation is to take, well, actually at 0 it has a derivative. So it's heading somewhere. It's increasing by a certain rate or decreasing by a certain rate. And you take this constant and multiply it by x. So that means that the first two terms together is the first order approximation, 0th order, and then first order approximation. But you can continue if you take the second derivative at 0 divided by 2. That's the coefficient in front of the x squared term. So why is it divided by 2? Well, because if you would compute for this approximate function on the right here, the second derivative, this is just a constant, this is constant, the 2 would be multiplied by x, so the 2 would disappear. So to approximate the second derivative perfectly, we need to divide the derivative at 0 by 2 times 1 actually. And in general, if we take n derivatives of x to the power of n, we will collect n times n minus 1 times n minus 2 times 3 times 2 times 1, the factorial of n, as the factor, to change the derivative at 0 to get the right coefficients in front of the x to the power of n term. And this just continues infinitely if we want to make the power series version of it. Now I say approximately equal here. If you end after a finite number of terms, there is also always an error term over here, which I will not describe. And also, even if you go on infinitely, this equation will not hold exactly unless you're close to 0. There is also always a radius of convergence within you must stay if you want the exact equality. For some nice functions like the exponential and the sine, then it's actually the whole real line, so you can go as far away as you want. But for some other functions like 1 over 1 minus x, where there is a pole, it's not defined for x equal 1, then the radius convergence is 1. Okay, and I will introduce in the next few slides a function that I called Dall as one of the parts to explain how you get this series from this f. So you could say, well, we see already how you get it. You described it here sufficiently much to program it, but I want to show that there are a number of steps in it and that the steps are useful by themselves. So the first step is to take the function f to an infinite list of the function and all its derivatives. And here I really mean all. It's an infinite list. So the first element is the function itself. The second is its first derivative, second derivative, nth derivative, and so on. And what type does this have? Well, I will introduce a type synonym here, ds, for derivative stream or derivative sequence. And generally speaking, ds has an argument. It's basically a list, and the argument type here is functions from R to R. So each element in the list is a function. I don't store just regular values here, but functions. So this is more on the semantic side, the mathematics side. Okay, so one of the things I can do with these functions is I can map the normal list map, the function apply 0. So apply 0 takes a function and just computes the value at 0. So after I map this, I get, instead of a ds of functions, I get a ds of just real numbers. F of 0, f prime of 0, f double prime of 0, and so on. So I now went from functions to just values at one point. But on the other hand, it's values at one point for all its derivatives. And then here, the last step is then to transform these coefficients a bit. So the function here takes a list of d's, and zips this list with division by factorial. So the 0th factorial is 0, the first factorial is, no, the 0th factorial is 1, first factorial is also 1, then the second factorial is 2, the third is 6, and so on. And the nth derivative here will be divided by n factorial. So the list factorials is the infinite list of the factorials of the integers 0, 1, 2, and so on upwards. And now I say we've got down to a power series of R. So why do I say we got a power series of R? Well, because we want these coefficients to be interpreted as the 0th coefficient, first coefficient, second coefficient in front of x. So we've made a transition from one function to infinitely many functions, to infinitely many derivative values at 0, and then to coefficients in a power series returning real. Okay, let's look at this first function a little more. So Dall. So Dall, the type of it is it takes a function from real to real to this data type ds of real to real, where this is isomorphic to it's basically a list. I will implement it in Haskell as a new type with a list inside it. It's a new type because it's not quite the same. I mean, it's the same type, that the internal list is the same type as I had for the power series representation. But the coefficients, the values in the lists are not the same. They don't have the same meaning. So that's why I'm keeping them separate here, ds and ps. Okay, and now I've added two arrows. So this arrow says that I know I can evaluate a funexp to a function from R to R. And then you might wonder, can we first compute a list of funexps and then map eval on all of these funexps? So can we compute from one functional expression an infinite list of the expressions describing the function itself as a syntax tree, the syntax tree of its derivative, syntax tree of second derivative, and so on? And now it's clear that we can compute it, but the question is, can we compute it as a homomorphism? Because then we can do many of these transactions. We can also make a type class for it. We can compute it in an efficient way. So this is intended to show it kind of a diagram that we can get from a funexp to an infinite list of functions either through first evaluating and then applying Dall, or by first computing lots of derivatives syntactically and then apply eval to every one of them. And we want these two ways to result in the same infinite list. So here I'm taking this apart a little further. I'm keeping the diagram below, and I'm looking at the first element and all the other elements of this list. So looking at the first element first, so I'm trying to specify here, we know that the function f should come back as the head of the Dall of f. So I'm trying now to specify what Dall should be doing. So the head, the first element of it, has to be the same function as came in here. So Dall has to return the same function first. Then if you look at this part, the blue bracket, that's a derivative and its derivative and its second derivative and so on. So the tail of the result here, so the tail of running Dall on f, it should be the infinite list that you get if you apply Dall to derivative of f. I mean, derivative of f, that's f prime. And you know that Dall will return first its first argument, f prime, that's this rule. And then its derivative, which is the second derivative of f, and so on. So actually, these two equations here specify Dall. I tell what the tail should be and what the head should be. And if I know what the tail and head is of an infinite list, that's all I need to know. And this is a way of summarizing one of these properties. So I want to compute oh, okay, now it should be a lowercase there all. So if you look at what's said down here, we have a lowercase there all. So that should take us from derivative to the tail operation. Now, okay, so this, sorry, it was not the syntactic, this is the d-all. D-all. Let's see if this makes sense. So I'm claiming that the d-all functions takes us from a derivative to tail. And what this is saying is that the first line here, so remember what h1 is saying? h1 is saying if I apply the function after this operation, I should also be able to apply this function d-all before, but then it might be another function. And usually we had these cases of a homomorphism where we transform one kind of addition to another kind of addition. So here, actually, what we see is that the derivative computation, taking the derivative, is represented by taking the tail of this ds of functions list. So if we do this transformation from a function to the function of all its derivative, or list of all its derivatives, then it's very easy to compute the derivative of anything. I mean, we sort of already done it. The d-all has done all the work for derivatives computation. So after d-all we need to do is just take the tail. Okay, so let's get a feeling for what this d-all is actually doing in some examples. So if we start with the identity function, it should first always return itself, its first argument, so that's the identity function. Then it should return the derivative of the identity function, which is constant 1. And then it should return, well, if you take the derivative of the constant 1 function, it will be 0. And here you could say 0, colon 0, colon 0, and so on, but actually we can also say 0 and define a 0 of this type to be either an infinite list of zeros or just an empty list. So we end there. Okay, if we take sinus, we know that the function sign, so this is not sign applied to some x, it's the function sign from real to real. This d-all should return first the sine function itself, then its derivative, which is the cosine, then the derivative of that, which is minus sine, followed by minus cosine, and then we go back to the beginning. The derivative of minus cosine is sine again. So this is an infinite list, but it's actually a repeating 4-element list. Nothing much happens, nothing interesting happens after 4 steps. It's a repeat of these 4 elements. These elements are all functions, but the infinite list is a repeat of them. And even simpler, if we would start out with the exponential function e to the power of x, well, it will return e to the power of x and derivative of e to the power of x and derivative of that and so on. So here we have an infinite list which repeats of just one element. So if I would have the same notation as the other one, it would be enough to say it's this and then goes back again. Okay, and now to illustrate this second operator we had in the chain, map apply 0. So if we have these lists, then we can also apply these functions and just take their value at 0. So let's check it for our cases. The identity function at 0 returns just 0. The constant 1 function returns 1. And the 0, well, there will be an infinite list of zeros or just an empty list there. So the infinite list that we get out is what we've indicated here in blue. Similarly with sine 0 is 0, cosine 0 is 1, minus sine is still 0, minus cosine is minus 1, and so on. So this representation after apply 0 is particularly easy. It's 4 normal numbers, not any complicated functions anymore, just 4 normal numbers and then repeat. And for the exponential, when we apply these two zeros, we always get just 1. So this is an even simpler example. And here it's worth noting that these are all of type, these blue things, so I should write in blue here, the blue things are of type ds real. So you might wonder what is this relation ds real to power series of real? But if this sequence of numbers 1, 1, 1 and so on should represent something as a power series, it would be, as we saw in one of the earlier lectures, the power series for 1 over 1 minus x. Because that has the coefficients 1, 1, 1 and so on as a power series. So it should say power series and not the Swedish word. Let's just erase that. But here, the same list of coefficients, just constant ones, is now representing the exponential function on the ds representation. So here we've got an example where we can use infinite lists to represent the function in two different ways. And in one way, we get one list of coefficients. In another way, well, we get another list of coefficients, or rather, for another function, we get the same list of coefficients. So, but as you saw also a few slides back, if we divide this by factorial, then we would get back the coefficients in this case. So if we keep dividing this, we will get 1, half, 1, 1, a half, a sixth, and so on. And that would be the coefficients of the corresponding power series. So we can, with a simple operation, transform between the derivative series and the power series representation. And I will show that in Haskell code in the next part.